The green hydrogen industry just achieved something that energy experts have been chasing for decades, and it could completely change the economics of clean fuel forever. Researchers at the University of Wollongong have developed an electrolyzer that reaches 95% efficiency, with some advanced systems consistently hitting over 90%. But before you get too excited about this breakthrough, we need to understand what this really means, why it matters so much, and whether these laboratory achievements will actually translate into real-world game changers for the hydrogen economy. Let's start with understanding what efficiency means in the context of green hydrogen production, because this is where a lot of confusion and inflated claims come from. When we talk about hydrogen production efficiency, we're measuring how much of the electrical energy input actually gets converted into usable hydrogen energy output. Traditional electrolyzers that split water into hydrogen and oxygen typically operate at around 70 to 80% efficiency, meaning 20 to 30% of the input electricity gets lost as heat during the conversion process. This efficiency loss has been one of the biggest barriers to making green hydrogen cost competitive with fossil fuels. The University of Wollongong breakthrough centers around what they call a capillary-fed electrolysis cell, which represents a fundamental reimagining of how we approach water splitting. Instead of flooding electrodes with liquid water like traditional systems, their design uses capillary action to deliver precisely the right amount of water directly to reaction sites. This eliminates many of the energy losses associated with pumping, heating, and managing excess water in conventional electrolyzers. The result is a system that can convert electrical energy to hydrogen with minimal waste heat and maximum efficiency. But here's where we need to be careful about interpreting these efficiency numbers. The 95% efficiency figure is based on what's called the higher heating value of hydrogen, which includes the energy released when hydrogen burns and the resulting water vapor condenses back to liquid. This gives a more optimistic efficiency measurement compared to the lower heating value, which only counts the energy from the combustion reaction itself. Most commercial systems and industry benchmarks use the more conservative lower heating value measurement, where even these advanced systems would show efficiencies in the 85 to 90% range. This distinction matters enormously for understanding real-world implications. When companies and researchers report efficiency numbers, they often use the measurement method that makes their technology look most impressive. A 95% HHV efficiency sounds revolutionary, and it is a significant achievement, but it's important to compare apples to apples when evaluating different technologies. Even accounting for this measurement difference, achieving 85 to 90% LHV efficiency represents a major step forward from the 70 to 80% typical of current commercial systems. The technology behind these efficiency gains involves several breakthrough innovations working together. Advanced electrode materials, including novel catalysts and nanostructured surfaces, reduce the energy required to split water molecules. Improved membrane technologies allow ions to move more freely between electrodes while preventing gas crossover that wastes energy. Better thermal management systems capture and reuse waste heat instead of losing it to the environment. Optimized cell designs minimize resistance and voltage losses throughout the system. Solid oxide electrolyzer cells represent another pathway to high efficiency that's showing tremendous promise. These systems operate at high temperatures, typically 700 to 800 degrees Celsius, which actually helps the water splitting reaction proceed more easily. The high operating temperature means these systems can achieve efficiencies over 90% on the LHV basis, and they can also utilize waste heat from industrial processes or solar thermal systems. Companies like Bloom Energy and Sunfire are developing commercial SOEC systems that could reach the market within the next few years. However, we need to understand the difference between electrolyzer efficiency and overall system efficiency. Even if an electrolyzer operates at 90% efficiency, the complete hydrogen energy system includes compression, storage, transportation, and eventual conversion back to electricity or mechanical work. When you account for all these steps, the round-trip efficiency of hydrogen energy systems typically falls to 40 to 45%. This is still much higher than it would be with less efficient electrolyzers, but it highlights why hydrogen is better suited for applications where direct electrification isn't practical rather than as a general energy storage solution. The economic implications of 90% efficient electrolyzers are substantial and could accelerate hydrogen adoption across multiple industries. Since electricity typically represents 70 to 80% of green hydrogen production costs, even a 10 to 15% improvement in efficiency directly translates to 7 to 12% lower fuel costs. For industrial users consuming thousands of tons of hydrogen annually, this could mean millions in cost savings. More importantly, higher efficiency brings green hydrogen closer to cost parity with fossil fuel alternatives, potentially reaching the magic $2 per kilogram threshold that makes hydrogen competitive without subsidies. Real-world deployment of these high-efficiency systems faces several challenges that laboratory demonstrations don't reveal. Durability remains a major concern, as many advanced materials and designs haven't been tested through thousands of hours of continuous operation under varying conditions. The University of Wollongong system, while achieving impressive efficiency, is still in early development stages and hasn't demonstrated commercial-scale production or long-term reliability. Scaling from laboratory prototypes to industrial-sized systems often reveals engineering challenges that reduce efficiency or increase costs. Manufacturing costs for advanced electrolyzers could initially be higher than conventional systems, potentially offsetting some efficiency benefits. The specialized materials, precise manufacturing tolerances, and quality control required for 90% efficient systems may command premium prices until production volumes increase. However, as with solar panels and batteries, manufacturing scale and learning curve effects typically drive costs down over time, especially for technologies with clear performance advantages. The timeline for commercial deployment of 90% efficient electrolyzers varies significantly depending on the specific technology. Some companies claim they'll have commercial systems available within 2 to 3 years, while others suggest 5 to 10 years for full market deployment. Regulatory approval processes, safety testing, and customer validation all add time between laboratory breakthrough and widespread adoption. Industrial customers, in particular, require extensive testing and validation before committing to new technologies for critical processes. Geographic factors will influence where high-efficiency electrolyzers have the biggest impact. Regions with expensive electricity will see greater benefits from efficiency improvements, since reducing electricity consumption directly cuts operating costs. Areas with abundant cheap renewable energy might prioritize lower capital costs over maximum efficiency. The optimal electrolyzer choice depends on local electricity prices, capacity factors, and specific application requirements. Integration challenges become more complex with advanced electrolyzer technologies. High-efficiency systems often require more sophisticated control systems, better power conditioning, and tighter integration with renewable energy sources. SOEC systems need thermal management and heat integration that conventional electrolyzers don't require. These integration requirements can add system complexity and costs that partially offset efficiency benefits. The competitive landscape is evolving rapidly as multiple technology approaches compete for market dominance. Traditional alkaline electrolyzers are improving incrementally while maintaining cost advantages. PEM electrolyzers offer operational flexibility that some applications require. SOEC systems promise highest efficiency but face durability questions. Each technology has optimal applications, and the market may support multiple approaches rather than converging on a single solution. Looking ahead, the path to widespread adoption of 90% efficient electrolyzers depends on solving practical deployment challenges while maintaining the efficiency advantages demonstrated in laboratories. Successful commercialization requires proving long-term durability, achieving competitive manufacturing costs, and demonstrating reliable operation across varying conditions. Companies that can bridge the gap between laboratory performance and commercial reality will likely capture significant market share in the rapidly growing hydrogen economy. The achievement of 90% electrolyzer efficiency represents genuine technological progress that brings green hydrogen closer to economic viability. While challenges remain in translating laboratory breakthroughs to commercial deployment, the direction is clear. Electrolyzers are becoming more efficient, and this trend will continue driving down hydrogen production costs. For industries that need clean fuel and can't easily electrify, these efficiency improvements could be the catalyst that makes hydrogen adoption inevitable rather than aspirational. The question isn't whether 90% efficient electrolyzers will become commercially available, but how quickly they can overcome the practical hurdles between laboratory success and industrial deployment. The companies and regions that successfully navigate this transition will likely lead the global hydrogen economy in the decades ahead.